Hi everyone, I am Hongyao Huang, and today I will talk about the convex hull complexity of uncertain points problem. This is a joint work with Benjamin Raichel. For a set of uncertain points U, each uncertain point Ui is a compact region in the plane. Natural cases are when regions are disks, segments, squares, etc. A realization of U is any point set P formed by selecting one point from each region. Here is an example of an uncertain point set modeled by a set of segments, and we select one point from each segment to form a realization. For the same set of uncertain points, there are many different realizations. For example, this is a different realization of the same set of uncertain points. We use real U to denote the set of all possible realizations of U. A convex hull of a set of uncertain points is the convex hull of a realization. Different realizations can lead to different convex hulls. For example, here we have a realization of this uncertain point set and its convex hull. However, if we have a different realization, we will have a very different convex hull. This raises the question, which convex hull are we looking for? Before answering this question, let me use one quick slide to talk about related previous work. There are different ways to model uncertain points. The way we model uncertain points has been used in several previous papers. And to answer previous question, people have considered different complexity measures of the convex hull. Specifically, previous papers have considered the problem when the complexity is measured by the perimeter or the area. As for our paper, we are the first to consider computing the convex hull with minimum number of vertices under such uncertain settings. Therefore, our problem is, given an uncertain point set U, select the realization P so that the convex hull of P has the minimum number of vertices. We focus on the case when the set of uncertain point is a set of line segments. Specifically, we consider a set of parallel line segments and a set of arbitrary oriented line segments. Our results include a cubic time dynamic programming algorithm when U is a set of vertical line segments. This algorithm also works for any set of parallel line segments. We also prove that it is NP-hard when U is a set of segments with arbitrary orientations. Now I am going to show you our algorithm, but before that I need to give some definition. We define a polygonal chain as an ordered sequence of points in the plane, denoted as P. P is monotone if for all I from 1 to n, Pi plus 1 has larger x coordinates than Pi. Respectively, we can define reverse monotone. P is convex if for all I from 1 to n, 3 consecutive points Pi minus 1, Pi, and Pi plus 1 defines a right turn. A right turn means Pi plus 1 lies to the right of the supporting line of Pi minus 1 and Pi. And here is an example of a convex monotone polygonal chain. Then we call P a top chain if it is convex and monotone. Respectively, we can define the bottom chain. Therefore, in the picture, the blue polygonal chain is a top chain while the red one is a bottom chain. Then the convex hull of a point set can be described by a top chain from PL to PR followed by a bottom chain from PR to PL, where PL is the leftmost point and PR is the rightmost point in the point set. Therefore, the input to our problem is a set of vertical line segments S. For simplicity, we assume that no two segments lie on the same vertical line, and the segments are ordered from left to right. We use Si plus to denote the top endpoint of a segment Si, and Si minus to denote the bottom endpoint. A set P with endpoints is a positive chain with respect to S if P is a monotone polygonal chain. P1 is from the leftmost segment in S, and Pm is on the rightmost segment in S. And all points other than P1 and Pm are the top endpoint of some segment Sj. The negative chain is defined similarly, but it requires that points other than P1 and Pm are the bottom endpoint of some segment. To design a polynomial time algorithm, we want to reduce the number of choices on each segment. In fact, we can argue that there is an optimal solution such that the top chain of the convex hull is a positive chain and the bottom chain is a negative chain. Here is an optimal solution example for this set of uncertain segments. Note that only segments defining vertices of the convex hull are realized at endpoints except for leftmost and rightmost segments. While for maximum area case, all segments are realized at endpoints. The difference makes it harder for us to achieve the same running time as they did. The lemma suggests a natural dynamic programming strategy. We can process segments from left to right. At each segment S, decide if it corresponds to a hull vertex. If so, take the top or bottom endpoint of S. If not, we maintain information about previous hull vertices such that the next vertex we select ensures S intersects the final hull. Hence, the realization of S can be on or inside the hull. Intuitively, we wish to maintain top and bottom chains of the optimal solution, but we encounter some difficulties to bring down the running time. First is that the top and bottom chains cannot be computed independently, because if the top endpoint is selected for the top chain, then the bottom endpoint of this segment cannot be added to the bottom chain. Therefore, we need to remember the last vertex selected from both the top and bottom chains. However, enforcing convexity would be more expensive, since it requires remembering the previous edge. This is why in the lemma we use positive and negative chains rather than top and bottom chains. This allows us to ignore convexity, which leads to a faster algorithm. Additionally, we ensure the positive and negative chain pairs we are computing is valid, so that the convex hull of such chain pair intersects all segments in S. Now we only need to compute the valid positive and negative chain pair with minimum number of vertices. Another difficulty is that selecting the point from the leftmost segment is more complicated, since it does not have to be the endpoints. We use min_ch_ij to denote the minimum cardinality valid chain pair where the previous positive chain vertex is Si plus and previous negative chain vertex is Sj minus. For now, we assume the leftmost segment S1 is a single point, so our initial call is min_ch_11. Since S1 is a point, S1 plus and S1 minus are the same. The base case is when there is a valid point on the rightmost segment, such that the previous vertices can directly connect to Sn. Valid means the hull will intersect all remaining segments to the right. We can determine if the valid point exists in linear time by turning into solving linear constraints over one variable. Otherwise, let P and N be the set of all possible next valid positive and negative chain vertices. The mean Chij equals to the minimum of two subproblems plus 1. The two subproblems are the minimum value for next vertex in P and the minimum value for next vertex in N. We showed in the paper set P and N can be computed in linear time. Our dynamic program runs in cubic time since we have a n-squared size table and each table entry takes linear time to compute. Now we are going to remove the assumption of S1 being a single point. We can argue that the optimal starting point lies in a set of n-squared canonical points on S1. The idea is that for a endpoint Sk+, P must be above the intersection of the supporting line of Sk+ and Sx-, because if P went any lower on S1, then Sx- would lie outside the hole, and there are only n-squared intersection points for all pairs I and j. If we simply try all such points with our dynamic program, it will be a n to the 5 times solution. Instead, we have an alternative cubic time solution with two cases. If top or bottom chain of the convex hull has no interior vertex, we can reduce to an easier subproblem. Otherwise, there must exist some pair of vertices Si+ and Sj- which are consecutive in the left to right order of the optimal hull vertices. Then we can independently calculate the minimal chains to the left and right of this pair with our dynamic program in cubic time. We also prove that it is NP-hard if the set of segments have arbitrary orientations. We use reduction from set problem. Specifically, given an instance of set problem with n variables and m clauses, we place n plus m points evenly along a circle in the plane. Imagine if we conceptually remove the convex hull of these points, then we will have a set of disjoint caps. These caps include m clause caps and n variable caps. We place points in both clause caps and variable caps. What's placed in the caps are more complicated, but I won't explain in the slides. Now look at the picture on the top. We construct this way because the pentagon is always in convex hull and we can focus on things inside the caps. Only complexity in the cap matters. If a variable appears in a clause, there will be a segment with one endpoint in each of the corresponding clause and variable cap. Our construction follows the hardness proof for maximizing the area case, but our problem requires more points in each cap, because minimizing things tends to pull the convex hull towards the center, while maximizing things pushes the convex hull towards the cap. To summarize, we showed a cubic time dynamic programming algorithm given a set of parallel uncertain segments. The algorithm computes the realization which minimizes the number of vertices on the convex hull. We prove that those segments defining convex hull vertices are realized at endpoint except for the leftmost and rightmost segments. We also showed the problem is NP-hard when uncertain segments have arbitrary orientations. This concludes my talk, and thank you for your time.